Welcome, everyone. For today's prep, I want to pick up where we left off in class. And what we were doing in class is we were looking at some examples of graphs of functions that all have a non-differentiable point at x equals 2. And there are kind of two categories here. There were the functions that had kind of a sharp change in the graph. So there was this example where we have this cusp at x equals 2. Then there's this example where we had a vertical tangent at x equals 2. The thing about those two graphs is we could trace over these curves in one continuous motion without ever taking our pen off the page. So same thing, well, if I could draw, there. We could trace over the curve in one continuous motion. Now, we also looked at a few other graphs where that wasn't possible. So we saw this example where there's a jump, there's kind of like this break and a jump in the graph. So as I start tracing, I'm tracing over, and then I literally have to take my pen off the page, put it down onto this point, and then I can keep going. Same thing, there was like an infinite jump here. So if I'm tracing the graph, I'm going up and up and up, and then eventually I just have to take my pen off the page and then put it down on the other side and keep going. And same thing, there was this third one where there was just kind of a point missing, a hole. And again, I'm tracing, and I can't trace over that hole because it's missing, so I literally have to take my pen off the page and keep on going on the other side. So these functions here, these we say are not continuous at x equals 2. So as we're kind of tracing over the graph, or as we're trying to draw the graph, if we ever have to take our pen off the page, there's kind of a break in the continuity. And so, whereas these graphs, these were continuous. So we're going to look at this concept. So continuity, the way we precisely define it, there's a limit definition. And what it says is that if our function f is continuous, so if this function's continuous, what happens at x equals a is that the behavior of our function as x gets close to a is equal to the function value right there at a. So we want to think of limits as kind of what's describing the behavior of our function as we kind of get close to, as our input gets close to the number. So this limit here, that's describing, this kind of describes f near x equals a. So what's going on to our function kind of around x equals a? And then on the other side, f of a, this is describing our function f directly at x equals a. So limits kind of tell us, kind of give us more of the story about what's going on around it. And then f of a is telling us, well, what's going on directly at that location. Now, intuitively, what this definition means is that our function is continuous if the graph doesn't have any breaks or gaps in it. All right, so we're going to look at an example where a couple examples where we check this. And when we check for continuity using this limit definition, there's three things we're going to check. So there's three things we need to check. So we're going to calculate the left-hand limit of our function. So as x approaches a from the left, we're going to calculate the right-hand limit of our function. And then we're going to calculate our function value directly at x equals a. And in order for it to be continuous, what has to happen is these three values that we calculate all have to be the same. So they all must match up. Okay, so let's try an example. Let's look at some graphs. We'll look at two. All right, so here's example one. We're going to determine whether these two functions are continuous at x equals 2 or not. And we're going to use that limit definition. So let's start with our first one here. We've got this graph. So there's three things we need to calculate. We need to calculate the left-hand limit. We need to calculate the right-hand limit. And then we need to calculate our function value. So we'll say directly at x equals 2. So let's do our left-hand limit. So we're going to do the limit as x approaches 2 from the left. So we put that little minus sign there. So if we're coming from the left, that means, again, find the number that we're kind of interested in. So we're interested in x equals 2. And for the left-hand limit, that means we're going to approach from this side of the graph. So graphically, the way we do limits is we imagine that you were standing on the curve here, and we're just going to take some steps along the curve here, moving towards x equals 2 in this direction. And we're just seeing where this curve is taking us. So it looks like it's taking us to this point here. And the y-coordinate for that point is 1. So that's the value of this limit. Limit would be 1 from the left. So we're kind of following the curve, seeing where the path is taking us. Now if we look at our right-hand limit, now x is going to approach 2, and we use a little plus sign there to indicate we're using values that are slightly bigger. Now for the right-hand limit, we're approaching 2 from the other side, but same idea. We imagine kind of going to the right side of the curve. Imagine if you were kind of standing up here, and we're just going to walk along the curve and see where this path takes us. And it looks like it's taking us to this same point. So if we follow the right side of our curve, it's taking us to the same point, and the y-coordinate for that point is 1. Okay, so far, so good. The two things we've calculated match up. Well, now we need to find what's going on directly at x equals 2. So this is where we're going to plug 2 directly into our function. And so to do this is where we look exactly at x equals 2, not a little bit to the left, not a little bit to the right. We're looking exactly at x equals 2, and we're trying to figure out where is the filled in point. And this point is missing. It's not part of our graph. The filled in point is up here, and the y-coordinate for that point is 3. So the output of our function here is actually 3. So because these values don't all match up, it's not continuous. So we say it's discontinuous. Since all three of those don't match. Okay. Well, let's try the next one. So what's going on in the next one? So similar graph, except now it's missing that point. So in this case, the left-hand limit and the right-hand limit, same as the previous one. So no change there. But now what about our function value? What about what's going on directly at x equals 2? So we want to plug 2 into our function. Let's see what we get. So if we go up, and again, we're looking directly at x equals 2 for this part, and we want to find the filled in point. This point's missing. It's not part of our graph. So it's kind of like it's a hole. We just kind of make it look bigger so we actually see it. If that one specific point was missing, you wouldn't even see it because the other parts of the curve would just kind of cover it up. So if only one point was missing from our graph, you wouldn't be able to see it. So we kind of artificially make that missing point look bigger there. So that point is not part of our graph, and if we keep looking, there is no filled in point at x equals 2. So this value we could say does not exist is undefined. A lot of times we abbreviate the does not exist D&E, but really undefined. So in this case, the left-hand limit and the right-hand limit still match up, but we've got a undefined point at x equals 2. So again, it's discontinuous, since all three values don't match. All right, so we're going to try a few more of these in class. But when you do the practice problem, want to see those three things all calculated. And once you get those three things all calculated, then you can kind of state the conclusion there. Continuous, if all three did match, we'd say it's continuous. If all three don't match up, then it's discontinuous or not continuous. Okay, so that'll do it for today's prep, and we'll see you in class. Bye-bye.